Testing. Although what disappointed me was, I went by this all since. Although what disappointed me was, let's just make this.
So folks online, Dr. Sievert's going to write with two different colors, black and blue. I shouldn't have told you. You could have guessed which one. Let me know if you could tell the difference.
Oh.
He's eager.
Like I can obviously see a pattern. I know the rules for it.
You cannot see the difference.
Yeah, okay, I just want to know which colors show up best. So I definitely need to stick to the black and the blue, but I can't like write in black and mark it up in blue because they can't tell the difference. Okay, good to know. Thank you.
Part of that is that they want me to collect all of your social security numbers. And for the internationals here, stay tuned. We'll see if we need anything from you. But so everybody else who is in the United States, please, I need your social security number, which means I can hang around during the break and I have it in a piece of paper. And that's possibly the best way, so we don't electronically, or we will figure it out. But so please, during the break, come and write me. If you feel comfortable, you can send it through Slack just to me.
People who are in the live stream, please don't send us your social security.
Okay. Hi, everyone. Can you hear me? Is it working?
Yeah.
Okay. So welcome back, everyone. Now we are going to resume our session of lectures. And Matthew Sievert will be talking again about introduction to QCD and small x physics. Feel free to raise your hands, ask questions as usual. And this is it. The floor is yours.
There we go. My audio is coming through okay? Yeah. Okay, very good. All right, thank you very much. It's good to be back for the second half of the lectures, now focusing on small x physics. It's a little bit strange to be talking about all of these calculations that I want to walk us through today, because we'll be talking about small x physics, but x isn't really going to enter the discussion at all. We'll really be talking about high energy scattering and probably only make the connection tomorrow about why that's referred to as low x. There's different terms, there's different definitions for what x is. They're all related to each other. But the common feature is QCD at high energies. And that's where we'll start today.
Recording in progress.
So last time we worked very hard to construct the QCD Lagrangian. We started off with the free multi-component Dirac theory, in which we had 3 quarks that came in NC different colors. For QCD, NC is 3, but for basically free, we can extend this to cover any number of quark colors. The quarks or the fermions of SU3 live in that fundamental representation, so they have 3 colors for QCD or NC colors in general. That's the fundamental or defining representation. For SU3, those were the specific Gelman matrices. There were 3 by 3 matrices, and there were 8 of them. The gluons live in the 8 by 8 adjoint representation of SU3. The adjoint representation is sort of provided automatically for free by the structure constants themselves. They also satisfy the algebra. So the gluons transform in the octet representation, the quarks transform in the triplet representation, anti-quarks transform in the anti-triplet representation, and you can make whatever kind of more complicated representations of QCD you want by taking different combinations of those groups. We also talked about the advantages of the large NC limit of SUN. It's particularly helpful because large NC favors your gluons. There are NC squared minus 1 of them versus only NC of the quarks. So if NC goes to infinity, you're essentially keeping only the gluons. And not only that, you drastically simplify the color algebra, effectively reducing your SUN back to UN, which means you don't have to worry about that pesky determinant condition anymore. Once we talked about the structure of the group itself, we found the conserved currents. It's just the particle number current, just like in QEV, but it's a particle number current along with a color rotation. So there's a different current for each possible color rotation you could have. And then once we found the current, then we knew how to do minimal coupling. We added that in, that gave us the definition of the covariant derivative. Once we had the covariant derivative, we were able to construct the field strength tensor. And once we had the field strength tensor, we had it all. We were able to put together the QCD Lagrangian in deceptively simple form in terms of gauge invariant interaction of the fermions with the gluons and the gauge invariant interaction of the gluons among themselves. So since we worked so hard to put this thing together, now let's apply it and do something with it. To actually do calculations with it, we have to translate this Lagrangian into the Feynman rules. Are we sharing?
Yes.
Yes, okay. So the Feynman rules arising from this Lagrangian are shown here. The interaction term contained in the covariant derivative, the one that couples this current to the gluon field A mu A, produces this Feynman rule. This one is pretty trivial. This one is just a simple generalization of the one that we already had in QE, where the vertex was minus IE gamma mu on the basis of the Dirac structure. The only thing that's different now is that we've added a color rotation, so the color matrix TA enters there as well. Not a big difference. From the interacting pieces of the field strength tensor itself, however, we get both the 3 gluon vertex and the 4 gluon vertex. The 3 gluon vertex came from cross terms between the free part, which involved the derivative, and the interacting part, which involved the structure constants FABC. That's why the 3 gluon vertex shows up as the color structure FABC, and it also shows up in a momentum-dependent way. That derivative that survived to contribute to the Feynman rule for this term gets translated into a factor of the momentum. So when you Fourier transform it, that derivative coupling means that you are sensitive to the momentum of the gluons coming in, and since the structure constants are anti-symmetric, they have an anti-symmetric dependence on the momenta as well. Finally, the 4-gluon vertex was built out of 2 of those interacting pieces. It enters at order g squared, so second order in the coupling. It's no accident that one vertex involving 4 gluons is of the same order as if you staple 2 of the 3-gluon vertices together. You can also make 4-gluon interactions by 2 of those vertices. You really only have to worry about this vertex if you're at high enough orders that you start having multiple 3-gluon insertions that start doing the same thing. The 4-gluon vertex is built out of 2 copies of the antisymmetric structure constants, and it's momentum independent because it didn't come from a derivative coupling. It just came from the certain components of the gluon field itself. So I can't jump into a calculation that uses these Feynman rules without talking about the most profound implication of what they do. The most important thing that these Feynman rules of QCD do is they transform the behavior of the beta function completely. The beta function, of course, describes the running coupling, the evolution of the coupling constant, since it depends on quantum corrections as a function of scale. As a reminder, if you have a bare particle, let's say a bare quark, then you would just have a certain amount of color charge. You would just have one parton in the system. But quantum corrections, quantum fluctuations dress this thing up. And it's not just a single quark, it's a quark surrounded by a halo of quantum corrections. Any interacting field theory will do this. And that inevitably means that the resolution that you have of all physical parameters depends on that momentum scale. Let's say 1/q sets the typical size of a measure. So if I measure at large q, then I'm really measuring at short distances. I see more of the original bare quark. And if I measure at low q, I measure at long distances and I see the quark plus most of its quantum fluctuations. This happens in any quantum field theory. It also happens in QED. In QED, the relevant diagram looks like this. You have the vacuum polarization of the photon. This says if I have 2 charges that are interacting by a photon, the vacuum isn't really empty. Sometimes out of empty space, you have virtual particles that pop in and pop back out. Those virtual particles in QED are electrons and positrons. And those electrons and positrons naturally fill up the vacuum with dielectric cycles. You have positive and negative pairs of E plus E minus charges that randomly pop in and pop out of the vacuum. So sometimes your photon is running along and it happens to hit one of those quantum vacuum fluctuations. And it spends some of its energy polarizing that vacuum. The effect is that the vacuum contributes like a dielectric in QED. It screens the interaction of the electromagnetic field so that it becomes weaker at long distances due to more screening and stronger at short distances. That's why in QED, the beta function increases as you go to higher Q, because you see more and more of the unshielded bare charge and less of the screening from the vacuum. But QED changes that behavior 100%, because in addition to fermions that enter the vacuum polarization, now you have all of the quarks, all of the quark colors, all of the quark flavors. You could have up quarks, down quarks, top quarks running around that loop. But in addition to fermions, now you have something qualitatively different. You also have the addition of gluon loops. And the gluon loops contribute very differently to the beta function. Unlike dielectric screening or diamagnetic screening in the vacuum from fermions, the gluons enter with a minus sign. They produce what you might call paraelectric or paramagnetic enhancement of the field as a function of distance. So there's a competition between screening from the fermions and anti-screening from the gluons. And depending on how many gluons versus how many quarks you have the ability to turn over the sign of the beta function from being fermion dominated and positive like QED to gluon dominated and negative. And it's not hard to figure out how many quark flavors you need. You need something really high, like 17 flavors before this thing stays positive. For QCD and for any sort of reasonable choice of those number of flavors, the gluons win. And that results in the beta function having exactly the opposite behavior. This is the most profound aspect of QCD, right? This tells you that instead of blowing up to infinity at short distances due to screening, right? You see less and less of the screening at high Q. Now you see the bare charge, which is not enhanced at high Q, right? So the opposite behavior of QCD is that this becomes weakly coupled at high momentum transfer, strongly coupled at low momentum transfer. The weak coupling at high momentum transfer is referred to as asymptotic freedom. This is the golden virtue of QCD. That's the reason it's so great. The price that we pay for asymptotic freedom is sometimes referred to as infrared slavery. It's essentially confinement. It's the fact that these things become infinitely strongly interacting at low momentum transfer. And that's telling you that quarks are not the right degree of freedom at low momentum. Just like in QED, you have a Landau pole, but that Landau pole is up at high Q. The Landau pole of QED is an indication that there's a phase transition somewhere up there at high momentum scales where the photon undergoes the electroweak unification. It becomes the electroweak force instead of just the electromagnetic force. For QED, that phase transition is in the UV. For QCD, that phase transition is in the infrared. This is the confinement phase transition. Somewhere across that divergence is where quarks start turning into protons and neutrons. So perturbative QCD can't describe what happens across that phase transition. But the benefit of it is that QCD is a well-defined weakly coupled theory to infinity. This is a critical property called UV completeness. And that is the thing that makes QCD so special. If you want to have any fundamental theory of nature, which is supposed to be the truth, right? Something valid to infinitely high energies, your theory needs to be asymptotically free. So this is the critical benefit of QCD. You have a theory which is self-consistent up to infinitely high energies because of its negative beta function. So QCD is very good at short distances and high momenta, and we pay the price of the confinement phase transition at low momenta to get that benefit of UV completeness. Okay. So having said a few words about what makes QCD so great, now let's actually use it for something. Questions? Yes, ma'am.
So kind of, this is the whole thing about the strong quarks having limited range, right?
Having limited range?
Yeah.
Yes.
Okay. Can you say again how this relates to the dress state versus the bare states and the distance?
Right. So the idea of the running coupling or the running mass or the running anything in field theory is that any quantum particle that you have when it starts to interact creates temporary quantum fluctuations around it. So you could be doing scalar theory, it could be anything. And those quantum fluctuations depend on momentum. So they depend on scale. And so when you measure the properties of the dress particle, right, this whole thing is the dress electron in QE, let's say. So this dressed electron would be the eigenstate of the exact Hamiltonian, the full interacting theory, if you could solve it. We can't solve it exactly, so instead we construct an order by order in perturbation theory, but still this is the eigenstate of the interacting theory. The elementary particle without the interactions is the bare electron, which is the eigenstate of the free theory, just a single non-interacting theory. So the point is you start off with a theory that looks like this, you calculate corrections to it to start constructing this. And when you do, you introduce spatial dependence because you introduce momentum. So if there's a cloud of, might be pions if you're talking chiral perturbation theory for protons and neutrons and pions, and you literally have a pion cloud surrounding the neutron or something. In the same way, you can have a photon cloud surrounding the electron. The cloud doesn't have to only contain photons, it can contain 2-bar pairs, anything that it can interact with. But the basic idea is that quantum interactions always produce a spatially extended system, even if you start off with something point-like. And that the running coupling, the running mass, renormalization as a whole is telling you how the effective parameters change as a function of scale. And for QED, the effect is the charge is largest at short distances because the quantum corrections have the effect of screening the electric field. So if you zoom in to high Q, you see larger forces. If you zoom out to low Q, you see weaker forces. And QCD does exactly the opposite because of screening. Instead of screening by the vacuum, you have anti-screening by the vacuum.
So when you go to, when Q gets high and beta turns low, that's what imposes this range limitation.
So just to make sure we're talking about the same thing, normally when people talk about the finite range of QCD, they're really talking about pions. They're talking about the fact that your proton and your neutron are effectively interacting by a pion, and the pion has a mass, so that the power potential that goes with this is not just a pure 1/r, but e to the minus m pi times r. So normally, I think when people talk about the finite range of the nuclear force, they're really not talking about quarks and gluons at all. They're talking about bound states, pions, and really long distance non-perturbative QCD.
So this isn't directly connected to range.
the finite range physics is what's across that phase transition. Right? The alpha S is the coupling of quarks to each other. And basically what happens is quarks are the right degree of freedom until this thing starts blowing up. And when this thing starts blowing up and becoming non-perturbatively large, that's when you have your phase transition, that your degrees of freedom should start changing to become protons and neutrons. And then you should get an effective Lagrangian that looks like this. But how exactly you get that out of the QCD Lagrangian is literally the million-dollar question. Okay. Other questions at this point? Yes, sir.
So in this graph, you have different legends, right? One for NLO, for NNNLO, and
Yes.
so what do each of these signify?
Oh, well, first off, it signifies that I stole this plot from the particle data group. Second, it signifies that they're combining lots of different measurements from lots of different channels and that they're all consistent with each other for the running of the coupling. So it's nice that you have JETS calculations. That's very sensitive to QCD details. Top quark loops are particularly heavy. You've got jets and jet shapes, heavy quarkonia, just the range of different kinds of observables that all are consistent with the same running coupling, and they all agree with the calculated running coupling from QCD. I'd say is a profound success of the theory.
But these are different orders of perturbation.
Yes, certainly that's what's said there. I don't know the details of those extractions. I don't know if that means, like certainly the theory curve here is a theory curve computed at some order in perturbation theory. Maybe to tie that to a particular observable, you need extra factors of the coupling. So maybe like NLO running coupling enters at NNLO for some observable up there. But they have to all be on equal footing, certainly, if they're describing the same theoretical curve. Okay, anything else? Okay, so let's step back a little bit from the grand questions of the meaning of life, the universe, and everything. And let's calculate something a little bit more concrete. It doesn't look like it, but this is our first step towards the discussion of the physics of small x. For the moment, let's just consider it as a warm-up exercise to start dealing with those Feynman rules that we just calculated. So let's try to calculate the process. Quark plus quark goes to quark plus quark, which is just elastic scattering of two quarks. In principle, there are two Feynman diagrams that I could draw in leading order. The first one involves momentum transfer by a gluon carried from, say, the projectile, which comes in and bounces off. That's then absorbed by, say, the target, which absorbs it and bounces back. This diagram is what I'll refer to as a T-channel diagram. And that's because the momentum transfer going through that gluon corresponds to the Mandelstam invariant T, which we nicely heard about yesterday. This diagram differs by swap of those final state particles, the final state quarks. That scrambles up the momentum flow. So instead of being a T-channel process, this is a U-channel process. And interestingly, it enters with a minus sign. Does anybody know why? Why is there a minus sign there? Yes, ma'am.
Fermionic fields anti-commute.
Exactly. It's Fermi-Dirac statistics. The fact that if I have two identical quarks in the final state, when I swap them, they have to be anti-symmetrized. So that's the reason for the sign that comes in. This is the total contribution to the amplitude. So for the moment, let's just practice those Feynman rules and set up this amplitude. The total amplitude IM is a sum of the T-channel amplitude and the U-channel amplitude. Let's start with the T-channel amplitude. So of course, you read your Feynman rules starting at the end of the fermion line and working backwards. So for this diagram, I start off with a spinner for the outgoing particle P1 prime. I'll denote that by the shorthand U bar 1 prime, just so that I remember which particle I'm talking about. The next thing that I have in the T-channel diagram is the photon, sorry, the electron, the quark gluon vertex. Gotta remember what theory I'm talking about. That comes in with Ig gamma mu Ta. And the Ta picks out a particular component based on the color states of the incoming and outgoing quarks. If the outgoing quark has fundamental color state I prime after the fact, and fundamental color state I before, that's the particular matrix element Ta I prime I. So that's the vertex. Then I multiply by the other spinner for the incoming quark U1. Now I do the same thing for the lower line. I have U bar of particle 2 prime. I have the vertex IG gamma nu TB, different color, J prime J, U2. And then I have a gluon propagator that connects them. The gluon propagator is minus I G mu nu delta AB over the momentum transfer P1 minus P1 prime squared for this diagram, plus I epsilon in principle, but the I epsilon is not relevant for us here. I should specify something important here, which is that I've written the gluon propagator in a particularly simple form, which only holds in a particular choice of gauge. This particular gluon propagator comes from the choice of Feynman gauge, or equivalently covariant gauge. The propagator can look different. It can be more complicated in different gauges. I'm just choosing the simplest one so that we can work through an example cover. Okay, so let's clean it up a little bit. The Feynman rules give me repeated indices. I can use the G mu nu to just raise that index nu to a mu. This is gone. The delta AB just tells me that the gluon color is the same when it's absorbed as it was when it was radiated. So that A is now the same as this A. I used up the delta AB. I've got I, and minus I. So overall my factor is plus I G squared. I have TA, I prime I, TA, J prime J. In the denominator, I have the Mandelstam variable T, different quantity than the generator's T here, sorry about that. And then the remaining spinor product is U bar 1 prime, gamma mu, U1 times U bar 2 prime, gamma upper mu, U2. Make sure I can follow that factors there. Plus G squared, TA, yeah, that looks pretty good. Okay, any questions on how we've employed the Feynman rule so far? It's pretty trivial to do now the same exercise for the U-channel diagram. Maybe I'll even skip writing it up on the board. You can see the only changes. Obviously, the propagator now depends on a different combination of momenta, P1 and P2 prime. So that instead of Mandelstam T gives me Mandelstam U. The only other difference is a minus sign. This minus sign is that minus sign, the fermion minus sign from interchanging identical particles. And now since I've scrambled up which final state particle connects with which initial state particle, I link up the colors differently. So I have TA J prime I and TA I prime J. Similarly, the spinors get scrambled up. I've got U bar 1 prime together with U2, U bar 2 prime together with U1. Yes, ma'am.
Or you can use the TAs outside of the U's because they're in a different state?
Yes. So, and because I'm writing them explicitly as a given set of components. You can get yourself into trouble if you keep these things as matrices and start commuting them around. But if you label out exactly which components you're talking about, then they're just numbers and they can move to everything. Okay. So this is the starting point. You could take this and you could calculate this process in any kinematic range that you want. By the way, Archites gave us a very nice introduction to the Mandelstam variables yesterday, but let me remind you just in case you need a refresher. The Mandelstam invariants are S is P1 plus P1 prime squared, sorry, P1 plus P2 squared. And by momentum conservation, that's the same thing as P1 prime plus P2 prime squared. Mandelstam T is P1 minus P1 prime squared, which is the same thing as P2 prime minus P2 squared. Mandelstam U is the one that's scrambled up between P1 and P2 prime, or between P1 prime and P2. You can also open up the parentheses here and express these things in terms of dot products. I will very quickly be working in the massless limit. And in the massless limit, all the squares are 0. The only thing that you have to worry about are the dot products. So I will immediately use this to write S equals 2 P1 dot P2 equals 2 P1 prime dot P2 prime, and so on down the line. You just pick out the cross terms from these products. as Archetypes challenged everybody to go give it for a homework problem, show that if you add up the three of these things directly from these definitions, not even requiring the massless limit, S plus T plus U is equal to the sum of all of the masses. And in this case, if I'm working in the massless limit, that's just going to be 0. So even though there are 3 Mandelstam variables, only 2 of them are independent. Generally, for this discussion, I'm going to relegate U to unimportant status, and I'm just going to talk about everything in terms of S and T, with U fixed by whatever it has to be for this. U equals negative T minus S. Okay, so we could try to calculate this process in any kinematic range that we like. The one that I want to focus on is the one referred to as Reggie kinematics. This is the one that has a connection to the physics of small x. So what does that mean? I'm interested in the limit of high energy scattering. What that means is I want to take the Mandelstam variable S to infinity. But I have to be careful about how I take that limit, because there are multiple ways that I can take S to infinity depending on what else I do with the other invariants. So I can achieve high energy scattering essentially in 2 ways. I can take option 1, which is S goes to infinity and T goes to infinity. Generally, T is a negative number, so I put an absolute value here. But you have this ability to take, let's say, both the center of mass energy and the momentum transfer to infinity simultaneously. This is the limit of high energy and high recoil. So this is a limit in which, even though S is going to infinity, you're still selecting a large angle scattering. This is very hard scattering processes. This is referred to as Bjorken kinematics. And in the context of deep inelastic scattering that I've not talked about yet at all, this is synonymous with large Bjorkenx. This is exactly the right regime that you want to be in if you want to focus on hard transverse momentum, hard scattering. But the regime that I want to focus on is the opposite case to this. Option number 2 is I could take S to infinity with T fixed. If I take S to infinity with T fixed, now I'm in a very different regime. Now I have a huge amount of energy coming down the beam pipe, but a fixed transverse momentum for the scatter. That limit where I fix, let's say, 1 GeV for the transverse momentum exchange, so I'm happily in perturbative QCD. But then I take S to infinity. That limit corresponds to the forward scattering limit. That's the limit when these quarks barely deflect at all, and they mostly go straight down the beam pipe because there's infinite energy coming down the beam pipe and only a finite transverse momentum competing. So this is the forward scattering limit. Theta goes to 0 in the center of mass frame. This is referred to as Reggie kinematics. And this is the one that I'm going to focus on. This is the one which is synonymous with small x. So I would like to start with this process and now simplify it assuming Reggie kinematics. The first thing that I do is I get to kill one of these diagrams. If I take S to infinity with T fixed, what is U doing? Fixed or infinity? Infinity. U is blowing up to infinity. It's actually negative infinity, but who cares? I have 1 over infinity in the 1 over infinity for the amplitude. So my U channel amplitude is totally irrelevant for the Reggie scattering process. U channel scattering typically describes back scattering, angles close to 180 degrees. So that's exactly the wrong region to care about if I want high energies and fixed momentum. So great, I only have now one diagram that I have to worry about, and I can further simplify that expression. So for quark scattering in Reggie kinematics, we only have the T channel amplitude, since the U channel amplitude is power suppressed. meaning it goes like 1 over u, which means it goes like 1 over s as s goes to infinity. This kinematic suppression by a power is way more severe than suppression by some fixed order in alpha s. In the business of QCD, you're lucky if alpha s is as small as 0.3. You can make s as big as you want. So this margin of suppression can be orders and orders of magnitude, which far, far outweighs any particular order of perturbation. So suppression by powers of the kinematics is way more important than orders of the calculation. Okay. Any questions before we go on to square this thing? Okay. So you may or may not be familiar with the cut diagram notation like this. Since I only have the T-channel amplitude, my overall amplitude squared, meaning I have to square the T-channel amplitude and then average it over the polarizations, average it over the color quantum numbers coming in and going out. It can be written like this. I'll discuss this in a moment. So the averaging which is being done here is an average over spins. I didn't write the spins explicitly on those spinners, but there was implicit dependence on the spin of particle 1, 1 prime, 2, and 2 prime. Here I have to average over the spins that are coming in. The incoming quarks can have either of 2 spins, so I have a 1/2 from the incoming quark down here, 1/2 from the incoming quark up there. And I don't care what the spin of the final state particles are, so I sum over them. You average the initial state, you sum over the final state. That's why I get a factor of 1/4, and I sum over all the spins. I do exactly the same thing for colors, and I can do this in an arbitrary representation, arbitrary SUN group. So if I'm working in SUNC, the incoming quarks can each have a color of anywhere from 1 to NC. And there's 2 quarks. Each one of those quarks comes with a 1 over NC from the averaging. So I get 1 over NC squared from the initial state. And now I sum over all of the quark colors, I prime I, J prime J. And now I have my T-channel amplitude squared. So now I take the amplitude that we had before and we plug it back in. So I get 1 over 4 NC squared, sum over all spins, sum over all colors. If I plug in the expression, I have I G squared over T, TA, I prime I, TA, J prime J, U bar 1 prime, gamma mu U1, U bar 2 prime, gamma mu U2. This was the T-channel amplitude itself, and now I have to multiply by the complex conjugate. The complex conjugate of the first factor is easy. I get minus IG squared over T. Complex conjugation also affects the generators. The generators are Hermitian matrices. So the complex conjugate of this is just related to the transpose of the adjoint. And they're Hermitian. So TA equals TA dagger. And therefore TAIJ conjugate is equal to TAJI. It's just a transpose. So when I get the color matrices with this, I get now a different color. I shouldn't reuse A, it's already summed over here. I get TBI prime, TBJ prime. I also have to complex conjugate the spinners. You have something similar here involving taking the adjoint of that spinner product. The final effect is basically that you just swap the order of the factors entering into the spinner product. So this spinner product, 1 prime gamma mu 1, becomes U bar 1 gamma nu U1 prime, sort of swapping which end has the U and the U bar. And similarly for the other one, you get U bar 2 gamma nu U2 prime. Okay. So now I can clean up all of the factors. Let's see, I have I cancels minus I, that's good. I have overall 1 over 4 NC squared hanging out in front. Now I have overall G to the 4th divided by T squared. My color factors now come into the color sum. So I have sum over the colors, which, let me write it explicitly, is I prime I, J prime J. This is TA I prime I times another TA I prime. And then I also have TB. Sorry, this one is TB. This is the other TA. This one is J prime J, and the other TB is J prime. And then I also have the sum over spins, which affects the spinor trace. So I get U bar 1 prime, gamma mu U1, U bar 1, gamma nu U1 prime, times U bar 2 prime, gamma mu U2, U bar 2, gamma nu U2 prime. Sorry, it's getting squeezed down here in the bottom. So the point of all of this explicit summation is that these get nicely assembled into traces. The spin traces are familiar to you already from QED. The sum over spins allow me to replace this with a trace involving the Dirac gamma matrices. And again, if you can't see something on the board or if I skip over it too quickly, the details are all in the PDF notes that you can get from the code. Right, so our spin and color averaged amplitude squared is given by 1/4 NC squared, G to the 4th over T squared. And now I recognize this as the product TATB, I prime after having summed over I. This is just a trace over the color matrices TATB. And likewise, this product is another trace of TATB. In exactly the same way, I sum over the spins. When I sum over the spins, I can replace U bar by the outer product, which is equal to the slashed momentum. So you have this nice identity, sum over spins, U of momentum P and spin S, U bar of momentum P and spin S equals P slash plus M. I'm working in the massless limit, so I don't care about the mass. But the nice benefit is that when I sum over the spins, this just gets turned into a P1 slash. This one and this one just get turned into a P1 prime slash. And these things are all connected together into a single trace. So that spin sum becomes trace of P1 prime slash gamma mu P1 slash gamma nu. And similarly, I get exactly the same kind of trace from the other spinor sum. So there I get P2 prime slash gamma upper mu P2 slash gamma upper nu. Exactly. I'm working in the limit when the energy is going to infinity, so a little tiny paltry mass doesn't matter. Okay, so let me make sure I didn't fumble a factor yet. Looks okay. All right, so the spinor traces are things that we already know very well from QED. The trace of 4 of these gamma matrices is simply 4 times P1 prime mu P1 nu plus P1 prime nu P1 nu minus, let's see, 2 of each of these, and no, sorry. This one, and then I've got this one, and that one, and then the cluster. So just the one. Minus G mu nu P1 dot P1 prime. And similarly, for this spinor trace, I get 4 P2 prime mu, P2 nu plus P2 prime nu, P2 mu, minus G mu nu, P2 dot P2 prime. That's all fine and familiar. The thing that's interesting and new are the color traces over the Gelman matrices. This is new information. The Gelman matrices satisfy a trace orthogonality condition exactly the same way that the Pauli matrices do. And after I've performed one of these traces, now I get a factor of 1/2 from this, and I get B equals A. The thing that I'm left with is the matrix TA times TA, summed over all A. If you think of this like a vector, this is a little bit like T dot T, which we'd say is the magnitude of the generator squared. In terms of rotations, the magnitude is its own separate invariant. It's something special like L squared that commutes with all of the components of L. In the same way, in this group theory, the sum over all of the generators, sort of the magnitude squared, is a special invariant of the group called the quadratic Casimir factor.
Dr. Sievert,
Yes.
would you mind staying away from the green? It's a little smeared looking on Zoom.
Sure.
You can make it out for now, but just.
Okay, I'll keep it for now since this is just a side comment, but I'll switch it up. Thank you. Right, so this is called the quadratic Casimir factor. It's often written CF, and for SUNC theories, it's the value NC squared minus 1 over 2NC. And if you plug in NC equals 3, which is the case for QCD, you get 4/3. It's just a special number that characterizes the group you're working with. So after I use this identity, then the thing which goes into my trace is this product. This thing is just a number. When I multiply those two matrices, I get trace of CF times the identity matrix. Well, CF is just a number that comes outside of the trace, and trace of the identity matrix is just the dimension of the space. Trace of the identity matrix is NC because it's an NC by NC identity. So at the end of the day, the color factor that I get is 1 over NC squared came from the color averaging. I had trace TATB, trace TATB. I use that first condition and I write it as 1 over 2 NC squared trace TATA. And then this is equal to CF times NC. So when the dust settles, my color factor is CF over 2NC. This is a very common color factor. If you start calculating various processes, it shows up all the time. This is the one for quark-quark scattering. It's just a number. If you plug this in, you have 4/3 for the case of QCD divided by 6. So this number is just 2/3, 2 lengths. Okay. So we're essentially done. We've plugged in all of the tricky parts. Now it's just some algebra to simplify it all out. Okay, so I have g to the 4th over 4t squared. We just calculated the color factor CF over 2NC. From both of those traces, I have a factor of 16 times P1 prime mu, P1 nu plus P1 prime nu, P1 mu minus G mu nu, P1 dot P1 prime times P2 prime mu, P2 mu plus P2 prime nu, P2 mu minus G upper mu nu, P2 dot P2 prime. Okay, so we multiply everything back out. Everything gets turned into dot products of the momenta. All the dot products of the momenta can be expressed simply in terms of the Mandelstam derivatives. So for example, this P1 dot P1 prime is equal to negative T over 2. It's exactly the cross term which shows up in the definition of Mandelstam T. This one, P2 dot P2 prime, is also negative T over 2. When I've got products of P1 prime and P2 prime, that's going to give me a factor of S. So this term, for instance, is going to give me a factor of P1 dot P2 and P1 prime dot P2 prime. This factor is S over 2. This factor is also S over 2. So this combination is huge. This is in fact the leading contribution. distribution, right? I have lots of different terms. Some of them are going to give me S, some of them are going to give me T, some of them are going to give me U. But in regikinematics, S is the one that matters. So when I expand it all out, I don't think I want to write everything in terms of the normal stem variables. It's just a bunch of algebra for nothing at this point. But if you multiply it all out, you get everything in terms of the Matt stem variables. You take the limit when S goes to infinity. And here, this is the final expression. So I get 4g to the fourth CF over 2nc, and the remaining kinematic dependence is S squared divided by T squared. Questions at this point?
What was the point of having two of the same?
Oh, yes, I didn't explain the cut diagram, sorry. So it's very clear to see from this level that when you write the amplitude squared, you can read off this final answer. It's a really useful way of double checking that you've done the right algebra by just applying the Feynman rules directly to the amplitude squared. So this has a simple meaning in terms of the optical theorem. We know that the amplitude squared, the thing we're calculating there, is related to the imaginary part of the forward scattering amplitude. That's exactly what's being drawn here. So because of the optical theorem, there's a one-to-one relation that says your amplitude squared is exactly the same thing as if I started off, say, on that top line and I started applying the Feynman rules. If I started applying the Feynman rules, I would get a P1 slash, a gamma, a P1 prime slash, and another gamma. And that's exactly what shows up here. These are the Feynman rules at the level of the amplitude squared. This is the spinor part for the upper line going across the cut, combining both the amplitude and the complex conjugate amplitude at the same time. It's a really compact way of talking about the probability as a whole, instead of talking only about the amplitude or only about the conjugate.
This one has to give you
Exactly.
the envelope.
That's right. That's correct. So this is just a visual way of applying the Feynman rules directly at the level of the amplitude squared to calculate a probability. So if you stare at that expression and you stare at the contents of those graphs, then you can convince yourself that that is in fact the color trace, which is represented in the spinor trace that's represented. Okay, so if this is the result for the amplitude squared, the last thing to do with it is to express it as a cross section. How am I doing on time, Mike?
I think we could.
We could
10
stop. Okay.
minutes.
If we're ready to stop, then maybe I won't belabor the algebra of actually constructing the cross section. There's a non-trivial step where you have to plug this back in. You have the standard expression for the cross section, which has 1 over 2e1, 2e1 prime, v1 minus v1 prime. And then for each of the final state particles, you've got d3p1 prime, 2 pi cubed, 2e1 prime, all this stuff. So you've got a phase space factor for each of the final state particles. You have the amplitude squared, and then you've got the momentum conserving delta function. The last bit of algebra that one could do is to sort of plug in for regikinematics. What are the energies? What are the velocities? What's the flux factor? What does my delta function look like? And then start with this and just integrate out all the redundant components. If you start from the definition, you can immediately integrate out all of P2 prime, using 3 out of the 4 pieces of the delta function to fix its value. The last part of the delta function, the energy conserving part, fixes the magnitude of P1 prime, but not the direction. And you're left with a differential. You're left with differential d2p prime, which is left over. So the cross section is a function of the one independent variable, the sigma d2p1 prime. That's the transverse momentum delivered in the scattering. And you see that it's proportional to alpha s squared, same color factor, and the momentum dependence is 1 over p perp to the 4th. This 1 over p perp to the 4th is the classic perturbative power law tail that you get from high energy scattering in QCD. The main thing that I wanted to establish with this calculation is that this cross section is energy independent. This is unsuppressed at high energies. I can take S goes to infinity, and this does not get small. It's small only by powers of alpha s, but because the scattering is mediated by gluons, the cross-section is unsuppressed. This is a unique feature of vector boson exchange. You would also get the same answer if you were doing QED. Basically, you just wouldn't get the color factor. But as long as you're exchanging a vector boson in regikinematics, you get the leading contribution, something that is unsuppressed. If you drew a diagram that had quarks in the T channel, or even worse, scalars in the T channel, anything with lower spin than spin 1, then you end up with an amplitude that's suppressed by powers of s, by 1 power of s for the case of spinners, 2 powers of s for the case of scalars. So high energy kinematics, the Reggie scattering, is dominated by gluon exchange. You can exchange gluons essentially for free without power suppression, whereas any other particle you would have to pay a major suppression factor in the air. So maybe this is sort of the first motivation towards gluon saturation, to say that the Reggie limit is a limit which is dominated by gluon exchange. And this is going to take us in the direction of creating more and more gluons and then scattering off of all of them by multiple gluons. So maybe this is a good place then to take a break and continue next time. Questions as we stand right now? Yes.
So we started off saying this is a quark-quark stack.
Yes.
Right?
Yes.
And then we said this at s tending to infinity and t being fixed.
Yes.
This is where the major contribution comes from.
That's correct.
And then amplitude was calculated for that.
That's right.
Now that amplitude, I mean, from the formula, it seems that amplitude goes to infinity as well, since s goes to infinity.
That's right, but there's also kinematic dependence entering into the flux factors in the cross section. So you can't only look at the amplitude, you also have to include kinematic dependence.
Might be the connection to the brain.
Yeah, so you're correct that the amplitude itself seems to become singular. It's a little bit maybe not obvious because you also have kinematic dependence in the spinners themselves, right? So I think you're talking about this. You say, you know, if t is small, then this is something which is large, basically. But there's also momentum dependence hiding here in the spinners, which is quite complicated. I think if you work it all out, you'll get basically a factor of s, that this thing goes like s over t at the amplitude level, so that you get something which goes like s squared over t squared at the amplitude squared level. But when you plug it back into the cross sections, there's a factor of 1 over s squared here in the flux factors. There's a 1 over s here in front, and there's another 1 over s here. So you cancel out the large factor of the s squared, and you're left with only the 1 over t squared that gives you the correct dimensional power counting for area divided by momentum squared. Right, other questions?
You said this is the feature vector boson.
Yes.
So here the vector boson is the one for this feature.
That's correct. So there's a really beautiful demonstration that you can calculate what the energy dependence is as a function of s for any cross section, only knowing what the spin of the exchange particle is. You can write it down for any j particle being exchanged, and then you can flip it on its head and say, if I measure a cross section with some energy dependence, let me infer what is the effective spin of the particle that caused that cross section. This goes by the old school name of Reggie trajectories, where you try to figure out what is the effective angular momentum of your particle as a function of scale. Now we have some idea of how old school Reggie trajectories actually correspond to gluons and such in perturbing QC. Okay, yes, sir.
You said that the cross section didn't depend on like the energy transfer, right? Or well, it didn't depend on like what the S channel is, right?
Yeah. The final cross section is independent of S. Yes.
So is that so does that also mean that's independent of Q squared? Because like at higher, yeah, because I imagine if you have
yeah.
like a greater, yeah, as I assume that the, you know, if your energy is going up, you know, your Q squared is probably going to go up, and doesn't the alpha S coupling go down as you?
Right. So I need to be really clear here about the dictionary between the S and the T in this 2-to-2 process versus the X and the Q squared, or the Q squared and the W squared we would talk about for DIS. For DIS, the Q squared is actually analogous to T. That's the transverse momentum scale that's being exchanged.
Right.
And S is the W squared. That's right. So you still have essentially the Q squared dependence, but Q squared is not the most important variable here. W squared here is being taken way, way bigger than Q squared. So I would like this to be, I don't know, a GeV or so that my Q squared is perturbative, but not infinitely small. And then I want to take W squared to infinity at the same time. That's how you end up with small x. Yes.
How does this say anything about the gluon saturation?
This by itself does not, but the calculation we're going to do next will. This is the lowest order calculation. Quark-quark goes to quark-quark. The next one is quark-quark goes to quark-quark plus blue. And the plus blue is going to be responsible for generating many more gluons. This is what tells you sort of the semi-classical baseline before you start generating quantum evolution with high energy. Maybe this is a good place to stop. I could use a drink of water.
Okay, let's take that.
All right, thank you.
Social security numbers here. What are they? Huh?
Yeah.
Let's see if this microphone works better than before. Okay, a few minutes later and refresh, we're ready for round two. We did lowest order. Now let's do next to lowest order. So last time we talked about the QCD Feynman rules, how they lead to the negative beta function. That negative beta function is what makes QCD a fantastic template for your favorite grand unified theory, whatever it might be, because QCD is our only UV complete theory that we know, at least the only one that we know exists so far. So let me say the non-abelian theories like QCD are our only example of UV complete theories. So there's no accident that one of the candidates for beyond the standard model physics is called Technicolor. It's basically just the hypothesis that what if something like the quark is not a fundamental particle? What if it's a bound state exactly like the proton and it's held together by a force kind of like QCD? That is again a non-abelian UV complete theory. So it could be turtles all the way down of protons inside of protons inside of protons with whatever level of complexity that you want. But whatever your UV complete theory of nature is, it's going to have a lot in common with QCD by default. We talked about two different limits of high energy scattering, regikinematics, the limit when the center of mass energy is much greater than the momentum transfer. In DIS language, this is equivalent to saying that the photon invariant mass W squared is much larger than Q squared. So this is the limit where Bjorken X is Q squared over W squared, which is small. None of this makes sense to you, by the way, if you don't already know about DIS, because I haven't told you, but just as a way of context for those who do. In contrast, for Bjorken kinematics, this is the limit where S and T are both comparably large together. That's the limit where Bjorken X is Q squared over W squared plus Q squared, and that could be any number of order 1. It doesn't have to be particularly small. So regikinematics, where it's forward scattering dominated, is synonymous with small x. Bjorken kinematics, what we normally talk about for DIS, where you're interested in large angle scatterings. The last thing that we talked about was a direct calculation of the elastic quark-quark scattering cross-section in regikinematics. The answer that we got was an expression for sigma dt. The Mandelstam T was that p perp squared. It was proportional to alpha s squared. It was proportional to the color factor, and it was independent of s as s goes to infinity. So it was constant and unsuppressed in regikinematics. And that's in contrast to the exchange of other kinds of particles. If you exchange a particle with spin lower than 1, you end up with a cross-section that is further and further suppressed with increasing energy. So gluons or vector bosons more general dominate regiscattering. Okay, the next thing that I would like to do is now calculate the first radiative correction to this process. So I'm interested now in regiscattering of two quarks off of each other where the final state contains quark, quark, and one gluon. So the scattering process is made up of 5 diagrams at lowest order. I could produce that extra gluon radiation in sort of 4 standard ways. You could have it emitted as final state radiation. These are these diagrams A and C. I could have final state radiation off of the projectile or final state radiation off of the target. Likewise, I can have initial state radiation off the projectile or initial state radiation off the target. All of this is also true for QED. I could have photon exchange and photon Bremsstrahlung. The part that's totally new and unique to QCD is this one, where the T-channel gluon itself undergoes Bremsstrahlung. And part of what we're going to do here is a detailed calculation at the rate things are going, probably only of diagram A, and then we will infer the answer for diagram B. We will happily get diagrams C and D for free by reflection symmetry from diagrams A and B, and then I will wave some hands and give you for free the answer to diagram E. Any questions before we dive on into the next calculation? Yes, ma'am.
Was UV completeness this idea of like that high momentum, the beta becomes small?
That's right. The asymptotic freedom is what makes QCD a UV complete theory. UV completeness means well-defined theory up to infinite energy. It does not break down necessarily just because the energy gets large. So the idea is whatever your fundamental theory of nature is, it is well-defined up to infinite energy scales. That is the true high energy theory of nature. Okay, so before we roll up the sleeves and start calculating all of these terrifying amplitudes, let me introduce a particularly helpful convention for the momenta. I meant to do this in the last lecture, but I was so excited about calculating the cross-section that I skipped it. You may or may not be familiar with what are referred to as light front or light cone components. Light front, also known as light cone coordinates or components of a vector. It's a really simple just change of variables. I define p plus or p minus to be 1 over the square root of 2 p0 plus or minus p3. All I'm really doing is just rotating my p0 and p3 axes. My usual space-time diagram has the time-like component up here, the space-like component on the horizontal axis. All I've done by defining these rotated coordinates is change those axes. So the p plus axis is the one which goes symmetrically along the time-like and the space-like direction. The p minus axis is the conjugate axis which goes in the other direction. Why do I care? Why is this useful? Because particles which are light-like, traveling at the speed of light, travel along a trajectory pointing along p plus. So it's very helpful to describe high energy scattering in terms of a particle moving with an enormous p plus momentum that's going at the speed of light along the positive z-axis. And by construction, a particle with large p plus has small p minus and vice versa. So these are especially useful for high energy scattering. And I should be really clear here. This is not the same thing as light front quantization. That is a completely different beast with its own pitfalls and dangers. Not the same as light front quantization. This is just a choice of basis for your vector components. You're free to do that however you like without screwing up how you quantize the theory. Okay, why is this useful? So for one thing, let me re-express the dot product of two vectors in terms of these components. If I just perform the change of variables from p0 and p3 to p plus and p minus, then the dot product looks like p plus q minus p minus q plus minus p perp dot q perp. You have this interesting kind of funny off-diagonal contribution in the light front components. That means basically that your metric tensor in terms of plus minus xy is off diagonal in this form. This also means, by the way, that if I have a vector component which is upper p plus, that's the same thing as lower p minus, because if I scramble up these components, that's how I raise and lower the indices for the metric. So p upper plus is the same as p lower minus and vice versa. I'm going to stick away from putting any of these indices downstairs. I'll always move them upstairs so that I have combinations of p plus, q minus limits. The light front components are very helpful for describing an on-shell particle moving at high energies. So if I have an on-shell particle, that means p squared equals m squared is supposed to be a constant. And that p squared, according to light front components, is 2p plus p minus p perp squared. And this basically lets me solve for one of the p plus or p minus in terms of the other. So for instance, I could fix the value of p plus, and then I know p minus is equal to p perp squared plus m squared over 2p plus. And this is helpful because, as you sort of anticipated from this diagram, if p plus is getting large, p minus is getting small. As p plus goes to infinity, the energy moving along the light-like axis p plus gets big, the amount of energy moving along the light-like component p minus gets small. So it's a very helpful way of separating out your large and small momentum scales when dealing with high energy scattering. And we'll definitely take advantage of that now for calculating this diagram A. Okay, any questions before we start applying the Feynman rules? Okay. All right, so I want to consider the scattering. Let me draw diagram A for concreteness. Oh yeah, I don't need to draw it on the board because I already drew it in. Okay, so let me set up this diagram in an analogous way to how we set up the elastic scattering at lowest order. I've got P1 coming in, P2 coming in. Those are the projectile and the target respectively. Now I'm producing an extra particle in the final state. So now I've got an extra momentum K, and I can't just call everything man, stem, S, T, and U. There's more momenta in the game, and I've just got to deal with it. So in addition to P1 and P2, I have the momentum transfer, which now I've called Q. I've chosen it to flow down, and I've called the momentum of the produced gluon K. So first order of business is let's specify the kinematics. I have high energy particles P1 and P2 coming in, they're on shell. I have high energy particles P1 prime, P2 prime, and K coming out. Those are also on shell. Let me choose a particular frame of reference for this. That way I know which is my large component and which is my small component. So I'm going to choose my frame of reference such that the large light front plus momentum is down here on the bottom. The large light front minus momentum is up here on top. So I'm going to choose that P2 minus coming in to be the large component. And I'm going to choose that the P2 plus and the P1 minus are the large components in this problem. This is basically saying I've chosen my coordinate axes such that the particle P1 is moving along the light front minus axis, and that's colliding with particle P2 coming in along the light front plus axis. So of course, I'm always allowed to do this. This is just a choice of reference frame. So as we just talked about, if I know that these are on-shell particles, then I can write my P1 mu, which has a large minus component, as whatever its minus component is, P1 minus. I choose my frame such that it has zero transverse momentum coming in. That is, I'm in a collinear frame to P1 and P2. So the center of mass frame is one example of this kind of thing, but it doesn't have to be exactly the center of mass. Once I specify P perp and P minus, that automatically fixes P plus by the on-shell conditions to be m squared over 2 P1 minus. Likewise, I have P2 mu. P2 mu is coming in with a large P2 plus component. It also has zero transverse momentum. And by on-shell conditions, its minus component is m squared over 2 P2 plus. And now if I close my eyes and don't think too much about how I'm violating my on-shell conditions, I can take P plus, P2 plus and P1 minus to infinity and write this as 0 P1 minus 0 perp, P2 plus 0 minus 0. So this is the massless approximation. The exact kinematics are this, keeping the mass. This is the one that prevents it from being exactly light-like. But clearly, if I take P minus to infinity, this one is going to 0, so it becomes light-like. And this is what the light-like momentum looks like. So this is just a way of separating out the large light-like momenta coming in along these different directions. Now, I can choose the kinematics of the scattering. I can also choose the kinematics I want to look at for the produced gluon. So I have a large P plus momentum down here, a large P minus momentum up there, and now I've got to decide where does the gluon go. The gluon could go forward to the minus going direction. It could go down the beam pipe along the negative z-axis. Or it could go down the beam pipe along the positive z-axis. The case that I'm interested in is when it comes down right in the middle. So not at forward rapidity, not at backward rapidity, but at mid rapidity. Mid rapidity is the case where this gluon is being produced with a plus momentum that is negligibly small compared to the big plus, and a minus momentum that's negligibly small compared to the big minus momentum. So the region of gluon momenta that I'm interested in is the mid rapidity production region. I want K plus negligibly small compared to the big plus momentum P2 plus. But it can't go all the way to 0. It's still got to at least be big enough that I don't screw up the other things that I called 0. It still needs to be much larger than the tiniest plus component, which is P1's plus component. Similarly, I need K minus to be much smaller than P1 minus, and I need that to be much larger than the tiniest minus component, which is P2 minus. This is my region of validity of the approximations that I'm going to need to use to do the calculation. Why do I say mid-rapidity? The definition of the rapidity is 1/2 times the logarithm of K plus over K minus. It's very convenient to write in lifelong coordinates. Yes, sir.
Should in the highest class approximation,
Yes.
should the first 0 be 0 plus?
Oh, yes, thank you. Yes. I just try to do that to keep track of which component is which. Thank you. Right, so why do I say mid-rapidity here? The larger the plus component and the smaller the minus component, the larger the rapidity, and vice versa. The rapidity is a logarithmic variable that basically on these light front axes, y equals plus infinity describes the light direction along the plus z-axis. Y equals minus infinity describes the light direction along the minus z-axis. And I'm talking about particle production right in the middle, not going down the beam pipe this way, not going down the beam pipe that way, but smack dab in the middle of your solenoidal tracker, where you have all of that nice particle. So this is mid-rapidity particle production, and you can literally get this in terms of the rapidity variable y. Okay, one other comment about x. This is a different x, which is maybe not obviously related to the x we were talking about a little while ago. The plus momentum here, being small in comparison to the big plus momentum in the problem, can be written as a momentum fraction, which is often called Feynman x. This is K plus over P2 plus, and the region that I'm looking in is the region where that is much less than 1. This is the x of this gluon compared to the target. You might, depending on your purposes, you might define an x1, which is the fraction of minus momentum compared to this. That's also small. This one is the fraction of plus momentum compared to this. That's also small. Mid-rapidity is nice because both the plus and minus components are small compared to the light-like axes. This is Feynman x. Feynman x is not the same thing as Bjorken x. Not exactly the same thing, but they are very closely related. Okay, I think I've probably said enough about the kinematics at this point. That specifies the incoming momentum. I now specify the outgoing gluon. The gluon is on shell. It's also massless. The gluon has some transverse momentum, and it has some K plus. On-shell condition fixes K minus to be K perp squared over 2K plus. This is not necessarily going to 0. K plus doesn't have to go to infinity, just because P plus does. K plus is much smaller than that. So here I have to keep all of the components. Those are non-trivial. Let me work out the on-shell conditions for Q mu, because that's maybe not obvious. Q is not one of the external particles. Q is the one being exchanged. So the on-shell conditions that fix the components of Q actually come from Q's role in the external particles that know about Q. So I need to use the on-shell condition for that particle and the on-shell condition for the other final state quark. So I can use those to fix the values of, let's say, Q minus. The value of Q minus is fixed by the on-shell conditions of the lower part of the diagram that has a large P plus. So I can get this from P2 plus Q's minus component, as long as I take away P2's minus component. P2 plus Q satisfies the on-shell condition, so that is Q perp squared plus M squared over 2 P2 plus Q plus minus, and then P2 minus was itself M squared over 2 P2 plus. And if I just stare at it for a second and say P2 plus is going to infinity, that one I can drop, which is effectively setting this to 0, which we said before. I ignore Q plus in comparison to P2 plus. This is also quite small. P2 minus, P2 plus is the large component. Yeah, that's right. Let me not set this to 0 too quickly. Q perp squared over 2 P2 plus. I think I could get away with calling this 0. I don't think I actually need the finite value for the rest of the calculation, but let me keep an eye on it for now. So this sets the value of Q minus from the on-shell conditions of the outgoing quark and the incoming quark. Similarly, I set the value for Q plus from the on-shell conditions from the incoming and outgoing quark on the top half. So Q plus I can get from P1 plus minus K plus minus P1 minus K minus Q. I think I've got it correctly what's written up there. P1 minus K minus Q, and then I add and subtract the necessary momentum that this gives me back Q plus. P1 plus is m squared over 2P1 minus. K plus is not particularly small. And this one is m squared plus K plus Q perp squared over 2 P1 plus minus K plus minus Q plus. And again, these things are negligible compared to, minus. The large minus components here. This overall thing goes to 0 as P minus goes to infinity. This also goes to 0, so the dominant contribution is this one. So I get Q plus is approximately equal to negative K plus. So this is basically a way of telling you how the large momenta are flowing through the diagram. The easiest thing is if the large plus momentum just goes straight down the beam pipe. You pay a penalty every time you want to send some of that momentum through the T-channel. This construction basically sends the minimum amount of plus momentum up through that gluon just to give you the kinematics you need for that emitted gluon in the final state. Okay, so that's how we fix the overall kinematics. Why am I belaboring the kinematics so much? Because the kinematic differences between diagram A and diagram B give the entire effect. We'll follow through how this actually works at the level of the Feynman rules in a minute, but the essential difference just comes from the kinematics of the intermediate state propagators. In diagram A, the intermediate state is that P1 minus Q. In diagram B, it's P1 minus K. Let's calculate what those are. So P1 minus Q squared. This is the one for diagram A. If I expand out that square in light front components, that's P1 plus minus Q plus, P1 minus minus Q minus, minus P1 perp minus Q perp squared. Let's see, P1 minus is the huge one, so I forget about Q minus in comparison to the giant P minus. P plus is tiny. How tiny is Q plus? Q plus is also pretty tiny. Let's see, so my P plus I took to be 0, my Q plus I have Q perp squared over 2 P plus. P2 plus. P perp was 0 by frame choice. So this just gives me 2, I have negative Q perp squared over 2 P2 plus. I have sorry. I'm with something here, 1 second. This is the minus. Oh, okay. I'm plugging in things in the wrong place. Sorry. Right, so by frame choice, P1 perp is 0, so this is just minus Q perp squared. I set the Q minus to 0 in comparison with the P1 minus. My P1 plus is tiny, my Q plus, however, is not tiny. Q plus is negative K plus. So this is positive K plus here. And I end up with 2 K plus P1 minus minus Q perp squared, and if P1 minus is going to infinity, I can ignore this term in comparison to it. Right, this is the large scale. So I have 2 K plus P1 minus is my evaluation of that virtuality. This is the off-shellness of this part. So similarly, I can do the calculation for diagram B. That's P1 minus K squared. So I get 2 P1 plus minus K plus, P1 minus K minus, again, only K has transverse momentum here. P1 minus is huge, so I ignore K minus in comparison. P1 plus is small, so I ignore that in comparison. And my K plus is just, it's just K plus. So I get minus 2 K plus P1 minus K per squared. And for the same reason, this is something finite. This is going to infinity, so I ignore it. The leading contribution is minus 2 K plus P1 minus. So we'll propagate this through the Feynman diagrams in a minute, but the essence of what's going to happen is already contained here. The kinematics of the scattering, the high energy kinematics, are identical for diagram A and diagram B with one difference. That one difference is the sign change of that intermediate state going from something positive, meaning time length. That's the one where the momentum is all flowing together. The plus and minus momentum are flowing parallel to each other in that propagator, giving you something positive. Whereas in diagram B, they're flowing against each other. This one was final state radiation, this one is initial state radiation, and that's exactly the reason for that minus sign in between. Okay, to whatever extent we have time for, let's plug some things in Feynman rules. How are we doing on time? Half an hour? Okay. Okay, so let's evaluate diagram A in detail. All right, so starting with the upper line, I have an outgoing spinner. Let me call that U bar 1 prime just for simplicity, the same way we did before. The first thing that encounters now is the gluon emission vertex coming from the final state interactions. So this is now the vertex IG epsilon / lambda star TA. Lambda is the polarization of the outgoing gluon, A is the color of the outgoing gluon. I'm not done yet. After emitting the gluon, or before emitting the gluon, but after in the expression I'm going to write, now I have the intermediate state propagator. So that is P1 / minus Q / over P1 minus Q squared. Now I have the interaction vertex of the T-channel gluon. This is another IG gamma mu TB, and then I end with U1. So that's the product along the upper line. I also have a product along the lower line. I have U bar 2 prime IG gamma mu. Let me call it gamma mu prime so I can write the propagator. TB prime U2. This is essentially the same as what we had before for the elastic quark-quark scattering calculation. And then I also have the gluon propagator in Feynman gauge, which is minus I G mu prime in this notation, delta B prime divided by Q squared. Yes, I didn't write it here, but you can also do quickly the other calculation. Your Q squared is just dominated by that minus Q per squared. You can sort of already see it here. Yeah, since your K plus is small compared to the P2 plus, when I square Q, this product, the P plus, P minus is small, the transverse component dominates. Okay, so I can clean this up. Sure.
In the top line, it's IG.
Yes. So I sort of took a shortcut here. What I should have done was call this gamma alpha or something, and then I should have had an extra part of the Feynman rule for epsilon lambda star alpha in the final state. This is the outgoing polarization vector for the gluon. And I just took a shortcut by immediately turning it into a slash inside the trace. Sure, no problem. Okay, so if I simplify the expression, I get IG cubed divided by Q perp squared 2K plus P1 minus. I have TA, TB, I prime I, TB, J prime J. I didn't carefully spell out the color indices here. If I had, then I would have said this is TA, I prime, I double prime. I prime is the final color. This is some intermediate color. On that same upper line, this TB is I double prime I. So when I combine the two together, I get I prime I overall, but with both color rotations in this order. On the lower half, I just have TB. And then the spinner part still remains. I have U bar 1 prime epsilon slash lambda star P1 slash minus Q slash gamma mu U1 U2 prime gamma mu U2. So I could proceed now the same way that we did before. I could calculate diagram A, diagram B, laboriously calculate all of the other ones, then square it and get all of the terrible interferences among the 5 squared terms. Much advantageous, however, if I can, to work at the amplitude level. Let me simplify this as much as I can now using iconokinematics at the amplitude level before I add everything up. How do I do that? It's not always simple to evaluate things at the amplitude level. But I'm really helped here by these iconokinematics. By the way, I think I started using this word without defining it. The iconal approximation is synonymous with regikinematics. This is again just another S going to infinity. Let's say in this case, P plus going to infinity, P2 plus going to infinity with I don't know, P2 perp fixed. You could do the same thing with plus or with minus. It's the same way of saying I have huge amount of momentum along the light-like directions, tiny everything else. The iconal approximation is the expansion in powers of S, essentially, so that I pick up the leading behavior as S goes to infinity, and you can think of it as a series where there can be power corrections in S beyond what we keep here. So if I say iconal, this is what I'm talking about. So how do I evaluate this thing at the amplitude level? Well, one thing that I can do is I can really simplify that spinner product on the lower half of the diagram. That's because that spinner product is a U bar of P2 prime gamma mu U of P2. And you know, yes, P2 and P2 prime are in fact different from each other, but they're not very different from each other. They have the same leading component. They have the same large P2 plus. So this matrix element is almost the same thing as U bar of just P2's plus component, gamma mu, and the same P2 plus. The fact that I can approximate this as having the same momentum on both sides means that I can evaluate it using a pretty simple version of the Gordon identity. The Gordon identity tells me how to evaluate in general a product like this, the U bar of P gamma U of P prime. There's 2 terms in the Gordon identity. There's some other messy stuff that comes from the difference of P2 and P2 prime. But for the case where they're equal, it's really simple. You just get a factor of 2 times whatever momentum you have. Right, so the Gordon identity, as I'm going to be using it, is U bar of P gamma mu U of P equals 2 P mu. And if I even put down spins, I could have different spins. This expression, as long as the momentum of this is the same, is diagonal with spin. Spin independent. So this is going to give me just the plus component, the large one, 2 P2 plus. I only get this if my mu is the correct vector index to give me plus for the answer. So I have to have a Kronecker delta that sets mu equal to plus. And I trivially get a delta of spins, S2, S2 prime. So once I can approximate, iconalize the lower vertex, now I know mu equals plus. Mu equals plus. And that helps me over here. Now I can plug this in, and I have gamma lower plus technically And I don't like lower indices, so I'm going to immediately turn that into gamma upper minus.
What does it mean for me to be plus or minus?
It's just a component of the vector. So just like you could have, PZ or P0 or something, these are the P plus or P minus vector directions of that one. Okay, so we've evaluated U bar of P2 prime gamma mu, U of P2 is approximately 2 P2 plus delta mu plus delta S2 prime.
Recording stopped.
Now-
Recording in progress.
Now I should work on the other matrix element, U bar 1 prime epsilon slash star P1 minus Q slash, and now I know this is gamma minus, and I have U1. Okay, so now I know which gamma minus component enters here. That helps. The next thing that I can do is simplify this slash momentum. The largest momentum which enters in here is P1 minus. So the large component is P1 minus gamma plus. There's also Q minus, but Q minus is negligible compared to gamma plus. If I had something different than gamma plus, if I had gamma minus, for instance, that would come together with things like P1 plus, but P1 plus is tiny. So just by doing the power counting in terms of the large and small momenta, I can pick out the dominant gamma structure of this term. And that's really nice because I can pull this outside. And now I get P1 minus as a multiplicative factor out front, U bar 1 prime, epsilon slash star, gamma plus, gamma minus, U1. Now I can take advantage of the equation of motion, the Dirac equation. The Dirac equation in the massless limit says P1 slash acting on U1 is equal to 0. Usually there's a P slash minus M, but I'm working in the massless limit, so I don't care. Similarly, if P1 is dominated by P1 minus, this statement is P1 minus times gamma plus times U1 equals 0. P1 minus is just a number. You can divide it out. This tells you gamma plus times U1 is equal to 0 with the light-like kinematics of the Dirac equation. That means if I take these two gamma matrices and I anti-commute that gamma plus over, I get 0. So I can, for free, replace it by the anti-commutator because the term that I'm adding to switch the order is 0. That anti-commutator is just 2g plus minus, which is just the number 2. So now I've killed 2 of the gamma matrices, and I just get a factor of 2 for my time. So I get U bar 1 prime epsilon slash star. Now I've got P1 minus in front and a factor of 2, and I just get U1 left over. And this is now again of the form that I can use the Gordon identity for. The epsilon is just another constant. This is 2P1 minus epsilon lambda star mu U bar 1 prime gamma mu U1. And if I use the Gordon identity to evaluate the large momentum on that line, this is just 2P1 minus delta mu lower minus delta S1 prime. So I have overall 2P1 minus squared, and then I have epsilon lambda star, just the particular component with lower minus, but I hate that, so I'm going to turn it into upper plus. And then trivially delta functions for the spins. So the Eikenham kinematics, high energy scattering, helps you a lot to work at the amplitude level and simplify these things down. I would not want to try to evaluate spinor traces or spinor products for general kinematics, but for high energy kinematics, it's not so bad. Time check, how are we doing?
5 minutes more, we'll say.
5 minutes more, okay then.
10 minutes.
Either way, it's time to start showing answers and doing less algebra. Okay, so we have all of the ingredients now. If I plug it all back in, my final answer is INA is IG cubed 2s over q perp squared epsilon lambda star, just the upper plus component divided by k plus. And then I have my color factors, TA, TB, I prime I, TB, J prime J. And then simple Kronecker deltas for the spins. Okay, this is the answer for that diagram A with the final state interactions. The calculation for diagram B goes exactly the same way, and it's only different in a couple of respects. Those only differences come from the intermediate state, that P1 minus K, which in the Eichenal approximation generates a minus sign. The thing that was 2P plus or 2K plus P1 minus before is now negative 2K plus P1 minus. So I'm going to get an overall minus sign here. And I have the fact that now those gluons are interacting in the opposite order. So the thing that was over here, first TA for the final state gluon, then TB for the scattering, is now first TB for the scattering, then TA for the emission. Because this is an initial state radiation, this is a final state radiation. So the only differences between these two diagrams are a minus sign and TBTA instead of TA. And this is already enough to allow us to draw very substantial conclusions about this process. Let me see what I have on the next slide. Okay, I have the answer and I've highlighted how they're different from each other. So these are the critical differences between them, and there's physics in this. This is telling you that high energy scattering has identical radiation for final state and initial state, but totally out of phase. So it's not like there's no emission. There is emission. Here it comes in with a positive sign. Here it comes in with a negative sign. But the direction of the incoming quark and the direction of the outgoing quark are identical to each other. The deflection angle is practically zero. So the radiation pattern here is sitting exactly on top of the radiation pattern there. And the only difference is a phase shift by pi from initial versus final state radiation. The other change that comes specifically from the non-abelian nature is the interchanging order of the color matrices. And this makes a huge difference. So just compare for a second, what does this mean if I have these amplitudes in QCD versus the same things in QED? So if I just add these two things together, MA plus MB, everything is the same. IG cubed 2s over q perp squared. It's exactly the same kinematics. Epsilon star plus over k plus. And the only thing that's different is that now combining the minus sign and the difference in the order of the matrices, I get a commutator. This object is commutator of TA with TB, I prime I component, which is I F ABC TC, I prime I. So this immediately tells you this combination is only non-zero for QCD. If you did this process for electrons in QED, you would still get the minus sign. The minus sign is kinematics, but you wouldn't have any color matrices. There would be no difference between this pattern and this pattern. And therefore, you would get perfect cancellation of initial state radiation and final state radiation in QED. And that makes perfect sense because everybody knows that to make an electron radiate, you have to make it accelerate. And if I have two electrons coming with infinite energy straight at each other and zero deflection angle, they didn't accelerate. So it's perfectly logical that in QED, there is no net power emitted in the form of photons. But in QCD, in any non-abelian theory, you have an internal degree of freedom. It's literally like, well, they didn't accelerate in kinematic space. They accelerated in color space. They rotated from one color to another. And because of that, they're different. So you couldn't be more clear. This is non-zero because the theory is non-abelian. And if the theory is non-abelian, it will be non-zero. So this is a uniquely non-abelian effect. The high energy Reggie kinematics are boring. They are trivial for QE, but they are exquisitely sensitive to non-abelian gauge theories like QC. If we had more time, then we would go through and we would actually calculate the cross-section for this. Before I show you the answer for the cross-section, let me point out another nice feature of this result. When we had the commutator that came out of adding these two amplitudes produced the structure constants FABC. And that rings a bell. FABC is exactly the color structure that appears in the triple gluon vertex. So it's almost like I added up diagram A and diagram B, and I got a weird version of diagram E. And since A and B are mirrors of C and D, if I add up C and D, I will again get a contribution of the same form. So QCD conspires to not only give you something non-zero, but to unify A, B, C, and D into the form of diagram E. And you can literally write it as if it were a strange 3-gluon vertex with a Feynman rule you can write down. This is called the Lipatov vertex, and it's a gauge invariant expression of all of those diagrams combined. That is the essential building block for small x gluon radiation.
Quick question.
Yes, go ahead.
So diagram E really has some very nice symmetry to it. Is that why we like to think of these in terms of this basis? But I imagine that we could represent it using one of those other diagrams,
You're saying,
hearing like that process.
You're saying diagram E is convenient by some choice? I don't think I understood.
I'm asking why is diagram E why is that one the one that seems to the generic diagram with our
Right.
point-like interaction? Why does that take the form of diagram E compared to the other ones? And is that related to the fact that E has this nice symmetry, whereas all the other ones are clearly antisymmetric in some way?
Yeah, I think that's essentially it, that the kinematics of A and B are identical but antisymmetric because of that minus sign. And so that's sort of, it's not going to look like A by itself, it's going to look like the combination of A and B to be something symmetric. I think you've got it right.
Thank you.
Okay. Right. So if I skip all of the squaring of the amplitude and just go right to the answer. So the overall amplitude has the form minus G cubed F ABC TC I prime I TB J prime J 4S over Q perp squared epsilon lambda star mu times the combination of momenta K perp mu over K perp squared minus K plus Q perp squared over K minus, K plus Q per mu, K minus K plus Q per squared. Yes. So this combination of momenta entering in along with the FABC, this is the expression for the Lipatov vertex. You can sort of read off from this what the effective vertex is. Then you calculate the amplitude squared, and you get 8 G cubed CF S squared over Q perp squared, K perp squared, K plus Q perp squared. Very nice, and then you can get the fully differential cross-section, d sigma, d2K perp, d2Q perp, dy, with y the rapidity of the emitted gluon, 2 alpha S cubed CF over pi squared, 1 over Q perp squared, 1 over K perp squared, 1 over K plus Q perp squared. Okay, so you get this nice answer. So what? The transverse momentum stuff is nice, it's clean, but it's very specific. This is very specific to the case of one quark scattering on another quark, where you get the sort of 1 over K perp to the 4th at large K perp, 1 over Q perp to the 4th at large Q perp. That's specific to the particular case of a quark scattering on a quark, which is not very realistic. Nature doesn't give us quark-quark scattering. That part will change if I make it, let's say, dipole-dipole scattering, which is something that would enter in light-by-light scattering processes. Or if I make it a realistic proton-proton scattering, that transverse momentum spectrum will change. The part that's robust, the part that I really care about on all of this, is actually the rapidity dependence, the dependence on the K plus. And if I look at everything on the right, with respect to that rapidity, this is just a constant. So forget about the transverse momentum stuff. That's going to be sensitive to the details of what system you're using. But soft gluon radiation in this mid-rapidity regime is independent of the rapidity. So you see explicitly that the cross-section is d sigma dy. Say you even integrate out the other momenta, you don't care about them. The rapidity dependence alone is just a constant. And that feature that describes particle production in QCD, it tells you high energy scattering radiates a uniform spectrum of soft gluons. As long as it's in the middle of the rapidity region, it doesn't matter what rapidity it is. And that generic prediction agrees fantastically well with experimental data on the rapidity dependence of particle production in high energy collisions. This is experimental data on inclusive hadrons in proton-proton goes to hadron plus X at CMS. And you see, as a function of pseudo-rapidity eta, the distribution of hadrons is practically a constant. It's not only a constant, it's almost a constant all the way up to the ends of the beam window, the beam rapidity. Detector acceptance cuts out here, but actual beam rapidity, I think, is like 5 units or so in each direction in this collision. So the prediction that we see from like tree level QCD is that you expect to get a uniform distribution of gluons everywhere in rapidity, in between the rapidity of the projectile and the rapidity of the target. So what does that do now for my total cross sections? Basically, what that gives us is, if I compare now my quark-quark goes to quark-quark glue, the radiated cross-section we just did, divided by quark-quark goes to quark-quark elastic cross-section that we did an hour ago. That ratio is down by a factor of alpha s, because in this process I had to radiate a gluon. But I also have to integrate over the range of rapidity that the gluon went out. So both of these are contributions to the inclusive cross-section quark-quark goes to quark-quark plus x. So I have integral of a constant from y1 to y2. This object is just y2 minus y1. And if you evaluate what that rapidity is, then this contribution from the NLO soft gluon radiation is alpha s log s over n squared. Which puts us in a very interesting situation where the coupling constant is small. In principle, the probability to radiate a gluon is small, but it has a very large phase space because it's allowed to radiate gluons anywhere across the entire beam rapidity. So if you have a high enough energy collision with a high enough rapidity, that rapidity, which is literally a logarithm of the energy, starts to compete with the coupling constant itself. And in the regime where alpha s is much less than 1, but the logarithm of s is much greater than 1, such that the two of them are not small at all. When that happens, I have to resum these contributions. This means the NLO radiated correction is just as important as the leading order elastic cross-section. And 2 gluon emission, as long as they're all sequentially ordered to all be soft, will also be just as important as the lowest order. And n gluon emission is all equally important, as long as everybody was soft compared to the one that came before. That gives you the picture of your original quark starts radiating soft gluons, and its soft gluons start radiating more soft gluons. And when I sum that series, I get an infinite cascade of a huge number of gluons, all of which have smaller and smaller momentum fractions x than the one that came before it. The same thing happens inside the proton. If you measure the proton structure at large x, it looks like 3 quarks. But as you go down and down in x, you start to radiate gluons, which start to fill up the proton with color charge. And those gluons radiate more gluons and more gluons and more gluons, until suddenly you don't have space to put any more gluons. They start interacting with each other very strongly. And this drives QCD out of the perturbative low density regime and into a regime that looks like many body physics. it looks like condensed matter, right? This is the regime of high density, high energy coherent scattering. And this is the phenomenon of gluon saturation that we are searching for. I'll end with the tantalizing plots. We see this experimentally. We see an absolute explosion of the gluon density as you go to small x, exactly as predicted by the boost invariant spectrum of QCD. We see that the structure function, which counts the total amount of charge inside the proton, is blowing up as you go to small x. And the question is, what happens in that small x region? What happens when my gluon density is already so high that I can't just ram off another gluon without thinking about it? That's the regime that leads to gluon saturation. And whatever time I can scrounge up tomorrow, I'll try to tell you about it. Thank you very much.
Questions for Matt?
Yes,
So is this like when people talk about color last condensate?
that's exactly it. So technical terms that I should have mentioned, but I forgot to. The evolution equation that resums these leading logarithms is called DFKL. That stands for Bolitsky-Faden-Kurat-Ipatov. This is the one that produces an exponentially growing gluon density. The evolution equation in the high density regime has several names associated with it depending on how it's formulated. It's formulated as the Jim-Walk functional integral equation at a mean field level. It's the Bolitsky-Kopchagov equation. You also sometimes see it referred to as the Bolitsky hierarchy of operators. The effective theory in this region, like when you are deep in the saturation regime, that you have that equilibrium point between radiating more gluons and reabsorbing gluons. That's when you're in the effective theory of high densities. Effective theory, and that's what's called the CGC, color glass condensate. It's the semi-classical effective theory where you're dominated by arbitrary number of gluons, but you still have a perturbative series with corrections to it. Other questions?
There was one over there.
Yes.
It seemed like you took when you showed the CMS plot, it seemed like you were taking a result from core scattering and applying it to proton.
Yes, that's right.
Why is that okay?
Because if you do the same calculation for different projectile and different target, you get different transverse momentum dependence, but you get exactly the same rapidity dependence. So I could do another perturbative calculation where it's all controlled. Protons are too hard. Dipoles are much nicer. So I can imagine like J psi scattering essentially, where I've got a tiny quark dipole, so that I can use perturbation theory for that. Then I get different transverse momentum dependence, but exactly the same constancy. And then I can take an arbitrary gluon distribution. I don't know what it is inside the nucleon, but I can calculate a radiative correction to it, and that radiative correction is always boost invariant. It's always, it essentially just comes from that light front wave function that I alluded to at the very beginning. This one building block already contains that rapidity independence. And so this ingredient going into any of the other calculations always yields that answer. Any other questions? Yes, sir.
Okay, so amongst all the Feynman diagrams you had, B and D happened before the collision.
Yes.
So then the fact that they are rapidity independent, it doesn't make sense.
B and D themselves are not rapidity independent, I don't think. It's only the sum of everything, right? There's this careful cancellation. Maybe I shouldn't speak too fast. Without looking back at the diagrams, maybe they are separately boost invariant.
But they don't even happen, I mean, they happen before the collision, B
Sure.
and D. So then how are you saying it's not even in the mid rapidity area?
Sure it is. You can have initial state radiation that happens before the collision vertex that just happens to come out at mid-50. Right, your incoming proton is radiating gluons everywhere the whole time. Right? Some of those come out at mid-rapidity. Your outgoing particles are also radiating gluons everywhere. I don't know. I don't understand why you say initial state radiation can't be in mid-rapidity.
So the detectors can also get the initial state gluon.
Yes. These are. You never know the difference, right? If you're doing your calculation and you want radiative corrections to it, you have to include both initial state radiation, final state radiation. They all contribute to your observable. They all have the ability to create particles that come out and land in your detector. It is a little bit weird to think about, how does the gluon coming out beforehand know what's going to happen later? But that's always present in quantum mechanics. That's a feature no matter which theory you're working in. Yes, ma'am. Ooh, yeah, so that's a really good question. Bjorken X is an experimental measurement that you make in deep elastic scattering. Bjorken X is specifically Q squared divided by 2 P dot Q. So in a given experiment, you measure a certain energy of the scattered electron, a certain angle. A given measurement corresponds to a given value of Bjorken X. So Bjorken X is a property of the experiment. Feynman X is a property of the wave function. Feynman X is, let's say, K plus over P plus. That's the fraction of momentum of a particular particle inside the proton. The connection between them is the DIS handbag diagram. When you actually calculate this thing, the on-shell condition for that outgoing port effectively gives you a delta function that gives you delta of X Feynman minus X Bjorken. So at leading power, leading order, like this, kinematics can be smeared. So it's not always as simple as X Feynman equals X Bjorken. But the idea is X Bjorken is a measurement, and the information contained in that measurement tells you about a snapshot of the wave function. You say, at this time, I hit something with X of 0.3. Oh, that must have been a valence quark carrying 1/3 of the proton momentum. Does that make sense? Yes, sir.
Is this X Feynman the same? I've seen C used in some textbooks as the sort of a priori momentum fraction.
Yes, depending on context. Sometimes C is used for something synonymous to X. For GPDs, it's used for skewness, which is related to X, but it's a difference in X. So yes, in general, but be careful depending on context. Thank you. Sure.
Not going to X.
That is this X with a shift that comes from having a large mass. So if you're doing deeply virtual meson production, then your on-shell condition has an extra mass that enters that shift. So the relevant X has this Nachman variable shift from the mass. Where, like, in order to put a J psi or something on shell, you have to deliver a minimum amount of plus and minus momentum to supply its invariant mass. So that's what provides sort of an extra shift on top of that. I believe that's correct. It's a little outside that.
Well, in the DS context, you have to go to large X, and the psi is a shift in. So you measure X Bjorken, and this is equal to X Feynman, right? At large X is different. At large X, X Feynman is equal to the Nachman psi, which is a shift of X Bjorken of the observable one due to the mass of the target.
Yes.
But at high energy or small X Bjorken, who cares?
Oh, I see.
The energy, the W square essentially is much larger than the mass of the target. Then who cares about the target? Who cares
Okay.
about the?
So it's still a mass shift, but it can come from different places. I'm familiar with it in the context of heavy vector mesons, but that makes sense. Thank you.
More questions?
Yes, sir.
Yeah, in your calculation of the two diagram A and B, they actually meet the longitude and the polarization one. So can I say that they are just here for gauging variance because I can choose a gauge, say light cone gauge to the limit.
Oh, I'm glad you asked about light cone gauge. Let me jump back. Yes, maybe this is good enough. Which longitudinal polarization were you referring to? Certainly not the radiated blue one.
The two amplitudes for A and B,
Yes,
MA and MB.
yes.
Yeah, they're actually class.
Yeah, so exactly. So this was a comment that I would have made if I had more time. Yeah, so this happens just because of the radiation here is coming from what I call the projectile. So the projectile has a large minus momentum. So the particular component of epsilon that it couples to is epsilon plus. You get P minus epsilon plus. And you're exactly right. If I wanted to, I could choose a gauge, a light cone gauge, such that epsilon plus is 0. In that gauge, I have, you will get A and B both equal to 0. And what that means is instead, A and B are 0, and you've moved all of the radiation down into diagrams C and D. I would prefer to do it the other way around. I would prefer to choose light cone gauge A minus equal to 0, because then C and D are 0. A and B and E are the whole story, and we've already calculated A and B. But you're completely correct about light cone gauge. That's a very useful strategic choice that you can make to simplify your life when doing a complicated calculation like this.
More questions? Okay, so this was a really good set of lectures, and it's not even finished. And you survived until now, not go back to the colleagues.